A flower pot falls off a windowsill and falls past the window below. You may ignore air resistance. It takes the pot 0.420 seconds to pass from the top to the bottom of this window, which is 1.90 meters high. How far is the top of the window below the windowsill from which the flower pot fell? This is a problem from University Physics by Young and Freedman. It's a first semester physics problem. This is a calculus-based textbook. This does not involve calculus, this problem itself. So as we read this, it doesn't give very much information. It gives us some time and it gives us some distance, and we kind of have a sense of some scenario, but there's not a whole lot to go off of. We do understand that it's a free fall problem, right? There's a flower pot and it falls off a windowsill, and it's falling and accelerating due to gravity as it falls past some windows. So we can go ahead and sketch this out just to kind of make some sense of what we have here. So it says a flower pot falls off a windowsill. So I'm going to draw a window. And it must have a windowsill, right? And here is my flower pot. And we'll go ahead and make the flower nice and green. And this poor guy is going to go for a ride, right? So it falls off a windowsill. And it falls past the window below. So we have to consider a window that's below. So I'm going to make a window below. This is just making a sketch to see if we can figure out what's going on in this problem. This thing's falling, and it's going to fall straight down due to gravity, right? And we're given some information here. So what information are we given? It takes the pot 0.420 seconds to pass from the top to the bottom of this window, which is the window it's falling past, the one below. So we're kind of led to take a segment here, consider a segment from here to here, the height of the window, the bottom window, and we're given 0.420 seconds as the time that it takes to fall that distance. And we're also given that the height of the window is 1.90 meters. So we can say this height here is 1.90 meters. And that's all we're given, right? So what is it asking then? How far is the top of the window below the windowsill from which the flower pot fell? So now we're having to consider a different kind of segment. So it starts here. That's the windowsill that it starts from. And it's asking, how far is that distance here? That's the question of the problem. How far is the top of the window below the windowsill from which the flower pot fell? Yeah. So here's our sketch. This makes sense. We have all the information we're given, but maybe there's some implicit information. We might as well assign an axis. This is a free fall problem. It's a linear problem. We don't have to consider a small horizontal velocity of any kind of rotation over the windowsill. We'll just say it falls straight down. And might as well make the direction of motion the positive axis. It's accelerating down, so I'm going to make positive y down. I teach all my students for these constant acceleration problems to sort all the information that's given and asked of you into this diagrammatic format, this diagram, where you consider a segment, and it's always going to be a horizontal diagram, even though sometimes problems have you moving down or up or spiraling, you can consider that all just a left to right progression. So I'm going to say this is the y-axis, positive y-axis. And here we can see that there's really like two segments. So I'm going to go ahead and split this in half and say that there's two segments here. And we can sort all of our information that we're given and that we don't know into this diagram like this. So I think it's pretty obvious, but here, this part of the segment corresponds to this corresponds to that part, and this here corresponds to the end of that segment there, right? So what information are we given? So the format of my diagram usually, I'm going to go with Y because it's a vertical problem, is we have a Y naught, we have a V naught, we have a time for this segment, we have an acceleration for this segment. Since there's two of them, I'm going to put one subscript there. And then we have a final y. I'm going to put a 1 subscript for the same reason. And we have a final velocity. And then for our second segment, we're going to have something similar. A2, T2, Y2, and V2. Right? So for each segment, we have this information. So let's see if we can sort out what we're given, right? So starting at the left, why not make that the origin and say that that's 0 meters? Sometimes when I rest my palm on the screen, it jitters the entire view. And if it's falling from the windowsill, it's falling from rest. That's something that's given that isn't really directly stated, but that's, we're pretty good at this, pulling out implicit information, right? So 0 meters per second here for initial velocity. Do we know anything about the time that it takes to fall from the windowsill to the top of the window below? We do not. So we can't write anything there. Do we know anything about the acceleration, A1? We sure do. There's gravity, right? There's gravity acting downwards. G. G itself is a positive constant, a positive quantity, and it's up to us to decide whether it's pointing in the positive or negative direction. Here, gravity is down, and we've taken positive y to be down, so A1, the acceleration on this segment of the flower pot, is going to be just G. All right, let's see. Moving on, do we know anything about Y1? We don't, but in fact, that's the ultimate question of the problem. Y1 is what we are ultimately going to solve. Do we know anything about the velocity when it reaches the top of the bottom windowsill? No, we do not, so we can't write anything down. Continuing on, the acceleration doesn't change. Gravity doesn't warble in or out or turn off. It's the same as the flower pot falls the entire length, so it's still G. Do we know anything about T2? Yes, this is where the problem gives us some information. So T2, the length of time just from the beginning of the second segment to the end, is 0.420 seconds. So this is not cumulative. I'm considering T2 to just be the time for that segment alone, which is important. You can take either way, but you have to be consistent. So that's the choice I'm making. Y2, however, since I've really done this along a certain line, I'm going to say Y2 is going to be a cumulative distance because this over here on the left really is my origin on a y-axis. And so Y2, it would be wrong to just write down 1.90 meters for Y2 because it's not. It's whatever the distance from the origin to Y1 is plus that 1.90 meters, right? So we can't write down 1.90, but we can write down something. We can write down what we just said. Y1, whatever that is, plus 1.90 meters. So this may feel a little uncomfortable because we would like to write down just pure numbers there and then use our equations to determine what the unknowns are. But we don't know that y2, that final distance, as an overall number. We just know a true statement about it. And with these more challenging problems, we'll take what we can get. We're going to distill all the true information into our diagram as we can. Finally, V2. Do we know anything about V2? We know nothing about V2. In fact, throughout this whole problem, velocity is probably the thing that we know the least and care the least about, because it's not asking for us for velocity and it's not giving us any velocity. So V2 is probably the least relevant quantity here. All right, so this is nifty. This is dandy, right? So in a standard problem, we would try to probably identify what we don't know nor care about and choose our constant acceleration equation, which I've placed up above here. We have 4 of them. And we try to choose the one that works for us to solve as directly as we can for the thing that we want. My students know that I like to organize these constant acceleration equations by what they do not contain for that very reason. Because oftentimes there's a parameter we don't know nor care about. And if that's the case, then we choose the equation that doesn't contain it, and we have a straight shot to what we want. So this first one over here, doesn't contain anything about position. It doesn't even contain anything about initial position. So I'm going to say no x. The second one doesn't contain anything about final velocity, but it does contain everything else. So no v. For that first one, it also doesn't contain, like I said, initial position, but initial position in our case and in most cases is going to be 0 because we're at liberty to take that where we want. Sometimes you have to take a specific reference point, but it's most instructional to think of that first equation as not containing final position because that's almost always non-zero. The third one, you can see, doesn't contain time, so no t. And the fourth one doesn't contain a, so no acceleration, no a. So that's how I like to think of them, right? So let's see if we can proceed the normal way. So looking at segment 1 here, the first segment of our 2-segment journey, we don't know very much. We don't know very much at all. We know that everything is 0 at the start, and we know that gravity exists, and that's about it. So if you notice, if we tried to build an equation based off segment 1, we're not getting super far. In fact, let's just try going through the equations. So with equation 1, if we were to try to attempt equation 1, we have V1, translating it to the notation of our problem, is equal to V naught plus, I'll go ahead and write G. It would be A1 times T1, right? We don't know T1. We do happen to know V naught, but we also don't know V1. And we also don't care about V1, really. I mean, if we have to solve for it, if we realize through the process of this problem that we have to, we'll do it, but it seems like maybe not the wisest thing to go charging off solving for something that we don't really care about, time or V1, right? So that's probably not our equation. So I'm going to go ahead and erase this. How about the second one? So writing out the second one in the terminology of our language, of our problem, we have y1, which really is what we ultimately are trying to solve for. So this is a good start. Equals y naught, we do know that that's 0, plus v naught t1, we also know that that's 0. This is looking pretty good. Plus 1/2 a t1. And that's a1, by the way, squared. We do know a1. We don't know t1. And y1 is what we're trying to solve for. So maybe there's something here, right? So maybe we can tidy this up. y1 is equal to 1/2 a and in fact, I'll just write g. G t1 squared. So maybe that could be helpful, but of course, it's one equation with two unknowns. And so we can't just directly solve for this, right? But here's a useful strategy tip. If you get somewhere that's really close to what you want and you find yourself thinking, man, if I only just knew this, or if I only had this or that, then I would be able to solve. Hold on to that thought, right? See if you can work backwards from that and actually figure out this or that you need, right? If you only had this, then it would be solved. Well, that's a lead on your problem, right? So I'm gonna think about that. I'm gonna think about that. If I only had T1, then I would be able to know how to solve this problem, right? Okay. Thinking about equation 3 and 4. So equation 3 involves V1, which we don't know about, and it doesn't include time, T1, and it involves final position. So perhaps that's equally as useful, but like we said, the velocity part of this equation, this whole problem, is probably the least relevant. We really don't know or care about velocity. Whereas time, we're given some time value on that second segment. So I don't mind that the T1 is sneaking its way in. And then finally, the fourth one, it cuts out acceleration, and that's the only thing that we know very straightforwardly for both segments. So that would cut out a lot of information that we know, and we don't want to do that. So that second equation for segment 1 seems potentially useful. It's not the whole story, though. So let's see if we can think about segment 2. So segment 2 now, maybe I use a different color. So segment 2 here, thinking about this, ooh, that's a thick one. Let's make them a little thinner. Equation 2, we can think through the exact same thoughts, right? So the first equation, v equals v naught plus at, we don't know final velocity and we don't know initial velocity. So that one's surely not our guy, right? And it doesn't even contain initial position, which in our case would be v1, which is what we're trying to solve for. So that one seems like an easy one to throw out. The second equation, final position is equal to initial position plus initial velocity times t plus a and 1/2 at squared. So that's potentially the thing, but again, we don't know v1. And unless we're going to go roundabout solving for v1 in order to solve for this random equation for the second segment, I don't think that that's going to help us much. The third equation, also equally unhelpful for the same reason. Velocity is in there, right? And the fourth one, the same. So for that second segment, the closest equation that cuts out the things that we don't want is the one that doesn't contain velocity, but it still has an initial velocity, which is not 0, that we don't know. And we'd have to kind of go take a scenic route to go find it. So even though there's a lot of information involved in this second segment, the closest that we can get is using this equation. Closest we can get is using maybe the second equation. I'll say here, y2 is equal to y1 plus v1 t2 plus 1/2 a2, which is just g, so we can give it that, times t2 squared. It is tempting though, right? Because we know about t2. That's a number. We know g, obviously. And what else do we know? We know something about y2, right? It's y1 plus 1.90 meters, right? So the y1s would cancel on both sides, and you get 1.90 meters is equal to v1 t2 times t2 plus 1/2 gt2 squared, and we know about t2. So maybe there's a route where we can do this, but I really like how neat and tidy this guy was, right? That's just one term. Exactly what we want, equaling to one term. And so if we can just find out what T1 is, that would be really helpful. So what do we do though? We've kind of exhausted everything. What do you do when you've exhausted everything that you think is given in the problem? This is probably what makes this problem a 3-dot problem. There's no straightforward path, right? We apply everything we know to get to where we want in the standard way, and look, this T1 is in our way. Or if we go the other route, this V1 is in our way, right? I guess I've gone the wrong way about underlining here. What I meant to do are little checks, right? Those aren't unknowns. The unknown is here and here, right? So there we go. So what do we do? And these have nothing to do with each other, right? So it would be really nice if this was an equation here that contained the same unknowns as here, but it's not the same. Y1 matches, sure, but T1 is not the same variable as V1. So this is not a 2 equations, 2 unknowns situation. It's a 2 equations, 3 unknowns situation. So that's not going to help. We're not done. So what do we do? Well, I know that these equations can be applied to any segment through which the acceleration is constant, right? And we've done that. However, check it out. The acceleration is g for both of them. It doesn't change from one segment to the next, right? So we've split this up into 2 segments because that's what we were led to do, because we want to know certain specific things about the first segment. But isn't it also legal to treat it as one big segment? Like this? Might as well try. So the initials are the same. Y naught, 0 meters. V naught, 0 meters per second. Now we have one big segment, and the acceleration is still going to be g throughout the entire thing. The time for this segment, well, now it's going to be T1 plus T2. It's the total time from windowsill to bottom of the lower window. So T1 plus T2, which we know is a number, 0.420 seconds. And then over here, the y final, that's going to be the same as we had it up above for y2. y1 plus 1.90 meters. Why is it that? Because that's the way we cataloged it up above. Remember, we were taking the entire 2-segment journey to be on the same y-axis, starting at the origin and building out. So the distance we kept cumulative. So that's the same. And then V2, which we can just write as V here because there's only one segment, we don't know about that. But again, we don't really care about that, right? Okay, so this is kind of a fresh look at the problem. And look at, we have actually a lot of information here. It's not straightforward. Like this is a true statement, but not just a simple number. And this is a true statement, but not a simple number. But we can deal with true statements that aren't just simple numbers. We can just throw them in there just the same, right? Why not give it a try? The police don't show up if, you take a wrong step in a math problem. So let's try it. So if we were to try to solve this, to apply one of the equations above to this segment, the only thing we don't know anything about is final velocity, right? So it would be foolish to try any equation that contained final velocity. So that's the variable we don't know nor care about. So let's take equation 2 then, right? So that would be y equals y naught plus v naught t plus 1/2, I'm going to just skip right to g t squared. Y naught is 0, v naught is 0, so those terms go away, right? And it almost looks like we have the same thing above, and maybe we've gotten off on the wrong track, because does it look like it might just reduce to the same thing and somehow another we haven't gotten any new information and we're just going to get two equations that are identical to each other? Not exactly, because what our y is different here. We're talking about a different segment, the overall journey, the two segments combined. And our t also is going to be different. So let's plug in what we have for each of those and eliminate those 0 terms. So y is actually, sorry about that, our y is actually, oh my goodness, y1 plus 1.90 meters equals 0 term, then we have 1/2 g, and then t, there's going to be a t squared term, and our t is equal to t1 plus 0.420 seconds. And that term is squared. Okay, so check it out. We have produced an equation with y1 as an unknown and t1 as an unknown, and that's it. And that's exactly what we have above. We have an equation here which has as unknowns y1 and t1. So that, in fact, is our system of equations to solve. We have two equations and two unknowns. And they are independent equations because they are pertaining to two independent segments or different segments. So they each present fresh information. So this is a system of equations, right? So that essentially is the key to the problem. We've gotten to the end of the puzzle part of the problem, and now it's just a matter of algebra finishing it out. But it kind of is interesting in one particular way, so let's talk about it. Let's finish it out. So the standard procedure, remember what we're actually trying to solve for is y1. And the standard procedure, if you have a system of equations, is to solve one of them for the parameter that you don't care about, plug it into the other equation, and then you get to solve for the one that you do care about. So that's the most direct path, right? But notice this one, I'll write it down below here. y1 is equal to 1/2 gt1 squared. If I were to solve that for t1, I get the square root of 2y1 over g, which isn't too bad, but then you consider that you have to plug that in here, and that term is squared, so that's going to be a quadratic. And yeah, t1 itself squared, not too big a deal, it just undoes that square root. But then there's going to be a linear term, and that linear term, if you plug in something with a square root, that's going to be some parameter to the 1/2 power. And that's just not a very straightforward quadratic to solve, right? So if I can avoid plugging in anything to like a quadratic formula or doing any kind of advanced algebra to solve these types of problems, I'm going to do it. So that would standardly be the approach, to plug in the one you don't care about to eliminate it. But that looked nasty. So maybe we do, in fact, take the scenic route here, because look how straightforward it looks to just plug what we have for y1 right in there. And then looks like maybe we'd be able to get t1 pretty easily, or looks at least like the path is cleared for us. And then we can take t1, plug it right back in here, and get y1. So that's my plan. So let's go ahead and do it. So writing this equation with this guy plugged in for it, right? So 1/2 g t1 squared plus 1.90 meters equals 1/2 g. And then we have to multiply this guy out. We have T1 squared, and then we're going to have 2 of these 0.420 terms. So that's going to be 0.840 seconds times T1. I'll just keep it open. Plus 0.420 squared, which I got to use a calculator to figure out. And I got 0.1764 seconds, right? Okay, I'm going to rewrite the left side again. Oh my goodness. To prove a point here, or to show something here, make it more clear. 1/2 GT1 squared plus 1.90 meters equals, so we're distributing this all out now. Do you see it? So we got that half applied, then we have G, and then we have T1, right? And we could even kind of keep it nice now. Plus, half of this 0.1764 number is 0.0882 seconds. And then that's times G as well. So times G. Okay. Do you see what I see? On both sides, we have a 1/2 GT1 squared term. So that goes away. And look how nice that is. It only leaves one linear T1 parameter to solve for. So this is pretty straightforward. T1 is going to be equal to 1.90 meters minus 0.0882 seconds times G divided by 0.420 seconds times G. And in fact, there's more G's than not. We can clean this up by dividing top and bottom by G. So we would get 1.90 meters over G minus just this nice simple 0.0882 seconds divided by 0.420 seconds. And if you plug that in, or you calculate that out rather, you get T1 being equal to about 1/4 of a second. So 0.2511 seconds. The sig figs for the problem are 3, right? For everything that's given, 3 sig figs. But here, this is just an intermediate result. Remember, this isn't what they asked for. This is what we now have to go plug in to find what they asked for. And so I'm going to take that extra sig fig to not accrue rounding errors. So if we plug this in, just like I directed, you get y1 is equal to 1/2 G times 0.2511 seconds, that's squared, and you get y1 being equal to 0.309 meters. And let's think about it to see if that's reasonable. It kind of seems reasonable, right? We're talking about windows. 0.39 meters. We're talking about the distance between windows vertically on a building, right? Does this seem like reasonable that this is 0.309 meters? I think so. The meter is 1.90 meters tall. Obviously, your windows can be spaced different amounts, but at least it's not like, 300 meters or something. That would be pretty unreasonable. And the units came out how we want. Right? So I'm going to say that sounds reasonable. Just a quick check on our work, right? And here is the answer to the problem, which initially seemed like we had not enough information to solve, right? So what this took was thinking about this problem in 2 different ways. We proceeded with the standard way. We realized we didn't have enough information to close it out in the standard way, or quote-unquote standard way. And so we had to back out and see, is there any more information in this problem that we're not realizing yet? What else do they give us? Because every which way we try a standard approach, we have too many unknowns for how many equations we can generate. So there must be something else, right? So you have to take a little bit of confidence and optimism in these problems and just believe that there is an answer. Sometimes that feels like not the case. Believe that you can get to the answer yourself. That's important. And just keep trying things. So keep going back to the source material of the problem and thinking about it. Maybe it takes making a sketch from a new angle. Maybe it takes, thinking about some other related physics that you have to bring in from some other, topic that we've learned about. But this is the type of thinking and problem-solving strategy that I would love to see out of my first-year physics students. This would be a rather challenging problem, but one that they have the tools to solve. And I found this to be a pretty pleasant problem because it presented as so simple up front, but it required a little bit of clever thinking, and it wasn't straightforward at all. All right, well, hopefully you got something out of this. Let me know if you did. Let me know if you were able to solve this before I got to the end of it. That's always really rewarding. And let me know if you'd like me to do another problem. I really enjoy all the problems out of this university physics textbook by Young and Freedman. And I hope you have a great day.